For functions defined on compact intervals, consider three statements. They can be either false or true, logical statements. F is absolutely continuous, which was defined through this summation of the variable differences less than delta implies the summation of f values difference is less than epsilon. Number two, that there is some L1 integrable function so that f is given by integrating g. It turns out that g has to be the pointwise derivative of f in the sense of calculus. Excuse me, derivative defined through difference quotients. And C, that f is actually a Sobolev function. It has a weak derivative, in this case that will be h, and that belongs to L1. F itself belongs to L1 if it's in AC. This is saying that with some other function h in L1, the integration by parts formula, which is this one, holds. This is called integration by parts because if f and phi were both C infinity functions, this would be just f prime, putting the derivative on the other one. So h kind of should be the derivative of f, and if we have an h where this holds for every smooth compactly supported function, we call h the weak derivative. And that is the classical Sobolev theory, not the Newtonian that we have been discussing. Okay, so we've seen before, and I'm going to recall that in a second, that A and B are equivalent. Today we want to discuss how they relate to C. Okay, before we move to C, let's see how A and B were equivalent. To go from B to A, that if f is given as an integral, why is it absolutely continuous, was simply because the integration operator was absolutely continuous. If you integrate over any set of very small measure, the integral has to be also small. From A to B, I'd say that it's basically Lebesgue differentiation theorem. And from that same theorem, it follows that if this formula holds for any function g, that g has to be almost everywhere equal to the derivative of f. Derivative again in the classical pointwise sense through difference quotients. If you have another proof avoiding the Lebesgue differentiation theorem, I'm very much interested in seeing that. But anyway, let's say we have proven the equivalence of A and B, which can be phrased as, because no one is going to remember A if and only if B. If you want to take a mental note somewhere, this will be that f and its derivative satisfy fundamental theorem of calculus if and only if f is absolutely continuous. So that's the message in this equivalence. Now let's switch to integration by parts. Ultimately, they are also equivalent to C. So C itself is equivalent to being AC, and so also equivalent to the fundamental theorem of calculus. But today I'm going to only prove the direction from A and B to C. Suppose we know A and B. We know that AC functions are exactly those functions for which the fundamental theorem of calculus holds. How do you prove that integration by parts holds? Of course, we have a candidate for this H, and that candidate is, well, the derivative of f. We do have a derivative. We just want to show that the derivative, almost everywhere existing derivative, does what it is supposed to do. That it is also a pointwise derivative. So goal to show integration by parts holds with f prime, i.e. the pointwise derivative of f. The pointwise derivative of f. Remember from B that this f prime is actually in L1 of a, b. So our weak derivative is going to be our guess, let's say, our candidate for the weak derivative. Therefore, we want to show, so in other words, we want to show pointwise derivative is the weak derivative. The weak derivative being defined again in the sense of Sobolev functions. Okay, where to begin? Well, take your arbitrary, compactly supported C1 function in AB. A tiny exercise is that phi is in AC. That's a very cute exercise using mean value theorem, for example. It's easy. And again, another elementary exercise in every homework for real analysis. If f is absolutely continuous, so remember we're proving a and b implies c, so we're assuming a and b. So f is absolutely continuous, phi is absolutely continuous, f times phi is absolutely continuous. That's another exercise. Now that we know that f phi, so this used the assumption A, that f was absolutely continuous. From B, which is follows from A, for every x in A and B, so any absolutely continuous function can be recovered from integrating its derivatives. So phi, f phi derivative, pointwise derivative, t dt from A to x. But remember that, so take x equal to b, then phi is 0 at the endpoints, right? So phi of A equal to phi of B is equal to 0. So all we get is that integral of f phi prime t dt from A to B is 0. But then the pointwise derivative, we have the product rule. You can check that this had nothing to do with more advanced stuff. It's again calculus 1 thing. When it comes to difference quotients, have you ever actually, by the way, proven product rule in your life? Or you believed in it in calculus and then never doubted that? Anyway, so this will be f prime times phi plus f phi prime dt. And if we rearrange that, we arrive at C. C, which is saying that integrating f against phi prime dt from A to B is equal to negative f prime phi dt from A to B. So C holds with H being played by f prime. That's end of the story. So we have shown that the pointwise derivative is a weak derivative, and also this belongs to L1, and f itself belongs to L1. So corollary to this is that if f is in AC on a compact interval AB, we use this compactness of interval in a few instances if you were being careful, then f is actually Sobolev function W11 of, I have to go with open interval. Sobolev functions are technically defined only on open sets. Okay, so C implying A and B, I leave it for you to investigate what is even the statement, what do we need to prove. But for now, we see that AC class is a subset of W11. The answer is that this is actually true and that these two coincide. So you may have seen it as saying that Sobolev functions on compact intervals of R are exactly the absolutely continuous functions. That is kind of the way it's usually phrased. Of course, one has to be precise because a function in W11 can change over a set of zero measure and it still be the same function. So that equivalence is implying that after changing the representative if necessary. From which also follows that W11 functions are actually continuous on intervals, which is not true in higher dimensions, as Sobolev functions can actually fail to have any continuity points. But that takes us far off topic. Okay, so let me know if you find this proof convincing and if you have any other questions in the comments. And by the way, welcome to many new people on the channel. I really appreciate you taking the time to subscribe, which is the best motivating factor that could be for me. Thank you a lot. Enjoy your weekend and see you soon with continuation of the Newtonian Sobolev functions.